Thank you, everyone. Welcome to my talk on attacking reinforcement learning via adversarial policies, current state, and future opportunities. That's a lot of words on the slides, but we'll break it down to a level that is understandable for everyone in this audience. I'm Wong Wai Tuck, and I'll be presenting this talk. Just a little bit about myself. As the host has mentioned, I'm a Ph.D. candidate at Singapore Management University. In that, I'm actually a researcher at the Systems Analysis and Verification Group, where we try to improve the soundness of the neural networks. My hobbies are playing CTFs and drinking a lot of beer and reading books and enjoying great music. So yeah, that's a little bit about myself. Okay, so I know I'm talking about machine learning in a cybersecurity conference, which is probably not the most exciting thing for you guys here, but let's try to motivate this a little bit. Hopefully get you guys interested in why this is important for us. So I'm going to state the most obvious thing, right? The use of reinforcement learning is actually all around us already. If you look at the recent hype around using AI to play games, right? To play Go, to play Dota, to play StarCraft, DeepMind is doing it, OpenAI is doing it, everyone is doing it. You know that AI can play games, and they can play games really well. They beat the best players, they beat everyone. So we know it's doing a really good job there, but playing games is not really useful, right? Like, we have real work to do. So we also have used reinforcement learning to get robots to do real work, like moving stuff. This is just an example, but in terms of real work, right? Let's say you don't want to drive your own car. Tesla has been using reinforcement learning to train their vehicles to do full driving, fully autonomous driving, and that's the beauty of reinforcement learning. And finally, if you like finance, a lot of the quant firms are interested in reinforcement learning because it is actually, when you're trading with different people, it's really just a game, and they've become really successful at using reinforcement learning to make a lot of money. So, of course, this is not very cybersecurity relevant, but just fun facts. But let's talk a bit about what reinforcement learning is changing the cybersecurity landscape. So recently, there's been a lot of thought of how reinforcement learning can change the way we think about cybersecurity. Because if you think about it, all your CTFs is just a game. If you think about a hacker in your network trying to get to your most sensitive resources or your most sensitive data, it's a game, right? They're just trying to enumerate stuff. That's why I'm in. I like CTFs as well, because it's really just a game for me. But just casting that idea that security is just a game is sufficient to allow the use of reinforcement learning to actually learn strategies to, for example, figure out if there is a way for an attacker to go into your most sensitive network data. So there's been some research work in trying to do this at a high fidelity, so you can see like representations of actual networks. Just a more concrete example, this is a research work done by Microsoft, where they actually have this game structure, and you could interact with the game through an API, and then you can actually get a model to actually figure out a policy to actually beat the game or to penetrate the system. So these things have become really high fidelity, and it's a bit scary because like our pen testers will run out of jobs soon, but that's fine. Of course, like it wouldn't be a machine learning talk if I don't mention ChatGPT. And we might be thinking, what does ChatGPT have to do with like reinforcement learning? But let's think a bit about what ChatGPT does. Of course, like we have seen how powerful it is. If you give it like a toy problem, for example, this toy problem where, hey, I don't allow addresses that are public to get the flag. Can you actually try to break it? And then ChatGPT gives you a really good answer. It tells you, hey, if you change the headers, you can magically get access to the flag. It gives you the correct answer, and you're really impressed by this. But what goes on underneath the hood is also reinforcement learning. So, of course, it's more than reinforcement learning. I'm simplifying a bit here. But the basic idea is they train a large language model. They use humans as a model to learn the rewards. For example, what is their preferences of like what kind of prompts they want to see. So if humans, for example, see a prompt that is really good, they'll give it a high score. So they train a model to basically pretend to be a human, and then they use that model to actually, as an abstraction, to query that, oh, is this prompt a good prompt for a human? So essentially, it's training to trick humans using reinforcement learning. So that's why you guys are so impressed by ChatGPT, because you guys are being tricked. But the ultimate goal of reinforcement learning, and one of the more exciting things that are coming up, is really human-AI collaboration, because AI is obviously becoming much, much more prevalent. It's becoming much better. Right? We have seen ChatGPT, and people, like my colleagues, have been using ChatGPT as a way of doing their work. But imagine if we can actually work together with AI, and there's been some research in using, for example, Overcooked, which is a very simple game. You play with your friends, you see, oh, how can you make your dish together, and it's using this model or this game to actually learn how to operate with humans better. So this idea is very powerful, and we are just at the very early stages of this. So with all this, I hope you guys are convinced that reinforcement learning is here to stay, whether it's in your ChatGPT, whether it's in your cars or whatever. But I'm not here to talk about how great reinforcement learning is. That's not the title of my talk. That's just the motivation. I hope you guys are motivated. But I'm here to talk about how it is broken. And for that, you need to understand a little bit of background. Right? I'm not going to go through the in the weeds, kind of math. I'm just going to give you a high-level abstraction that everyone can sort of understand. There's some math here. I'll make some pretty pictures to make sure that everyone understands what this is. So the basics of reinforcement learning is that there is some player or agent that's interacting with some environment, be it a game or whatever. So the very classical example of an agent, let's say you're playing Flappy Bird, which is my favorite game. So you are a bird. The agent is the bird. So in that game, you can basically do two things, right? You can either press the screen and you jump, as you can see here, or you don't do anything and the bird just falls down. And that's basically an action. Your agent, your bird, is interacting with the environment, and maybe you cross some pipe in your way through, and your target environment tells you, hey, your score increased by 1. So that's the reward. And finally, once you perform an action, of course, the location of your Flappy Bird changes, so the state is updated, and now your agent or the bird has to figure out what to do next. Right? Should it jump? Should it not jump? If it jumps, will it die? Etc., etc. So there's one thing I missed out talking about here, which is this very big math sign, pi, theta, with a dot. You might be wondering what that is. That is what we call a policy. It's something that an agent uses to decide if I am in this place, what should I do? So what is this policy? It's basically a function. It takes in whatever input, which is the picture of the Flappy Bird environment, and it decides, what am I going to do next? Am I supposed to jump? Am I supposed to not do anything? So that graphic in the second line should tell you roughly what that function pi would look like. That's called a policy. So it's a function. We don't know how to express it. Do I define it in Python, def, policy, and then if I'm close to a pipe, I do this. That's something we can do, but machine learning experts like to do it in a much easier way. So this function is something that we want to express, but we have no easy way of expressing it or defining it ourselves. And that's where we use the power of neural networks to create functions that we can arbitrarily optimize into the functions that we want it to be. So let's go into a bit of neural networks, because neural networks are the things that we need in this part so that we are able to get the results that we want. So neural networks are basically things, these neurons connected, and then it takes in some input and it has some output. And there are hidden layers in the middle, right? You can think of them as, in the next slide, which will show you what they actually are. So essentially, there are just a bunch of weights attached to the input. And for example, some number 4.3, 1, etc. And then the basic idea is you're just trying to find the right numbers to fill in those slots. So this is basically machine learning. It's just numbers. I wish I was lying, but this is the truth. So the beauty of neural networks is that once you have these magical numbers, you add them together based on some input, and you have enough of these numbers, and stack them up long enough with what they call a non-linearity layer, like a ReLU, rectified linear unit. What you get is actually a very nice theorem in that these neural networks can approximate any function in the universe. So essentially, once you learn the right W, you can get a magical policy that will tell the Flappy Bird exactly what to do in that state. So going back to this original picture, we didn't know how to define the policy which takes in some state and gives us the action of what to do. So we use the beauty of neural networks. We just put this there, and then we just find the right W. That is outside of the scope of what we will talk about today. But essentially, once you find the right W, your Flappy Bird will know what to do. So we now know reinforcement learning. That was a quick crash course. Everyone knows neural networks and reinforcement learning now, yes. But how do we even get to this state in the first place? So we need to go back to a very long time in history with a very simple toy example. So in the past, people were primitive. They played very boring games. So this is one of the games they played. It's not Pac-Man, but it's like before Pac-Man. So they are trying to get to the point where there is a diamond. So how do you solve for such a game, right? This is a very complicated game. They come up with this notion of a Markov decision process, or MDP. So what this is a bunch of things. There's some things there, but essentially it tells you, it defines, okay, which cell are you in? For example, these are the states. What actions can you take in each of the cells, up, down, left, right? And then it tells you where do you get your reward, and then it tells you what happens when you take an action in that state. So all these things are very well defined here in this simple grid wall example. Then this is everything you need, right? Like, when you have everything, everything becomes simple. Even I can solve it right here. I think most people can. If you use programming, you can do like breadth first search, depth first search, all those name dynamic programming stuff. But I'm just gonna just do this, and you solve the game. Yay! Yes, it's trivial. So MDPs solved, easy. Everyone knows that this can be solved. This is like the early state of the art. But let's have a new challenge, right? This is too simple. This is like baby cake. New challenge. Let's make it a bit harder. So in our new game, right, this robot can only see a limited amount of things. Like, it cannot see the entire grid world. It only can see ahead and to its left and right, and whether there's a wall. So if you look at this robot right here, what it can basically see is that in the north and east and west, there is no wall. And in the south, there's a wall. So this severely limits the observation space of this poor robot, because now it has no idea where it is, right? To give a more concrete example, let's say this robot is here, then basically there's a 0.5 chance that it could be either on the top or the bottom, if it's facing here or it's facing here. So this is what they term as a partially observable Markov decision process. It's very similar to what we saw just now, but there's a huge difference, right? Instead of being able to observe what is the state of the world, you only get partial observations of what is actually happening in the state. And the trick here is that, how do you solve for this? You basically have to trust yourself. You have to believe that you are in this particular state. So you have a probability distribution or confidence on where you are in the world. And then you can solve it like a normal MDP. That's in theory. But can we actually solve this? And it turns out, once you limit the amount of information that you can see, like even that thing that we in this simple example, it's 11 dimensions, in fact, and it's continuous because each probability attached to each cell is from 0 to 1. And actually, none of the algorithms that we talked about earlier can actually deal with this. And it turns out that this is actually very difficult to solve. It's p-space hard. To give you a notion of what is p-space hard, so you have your quantum computers which solve bounded quantum polynomial problems, and they can solve factoring of RSAs. That is not as hard as NP-hard. So NP-hard is a bit harder. NP-hard is like you can brute force everything and then you can solve it. So your quantum computers, and then there's the NP-hard, and then p-space hard is even harder than both NP-hard and your quantum computers. So this is something that even quantum computers cannot solve, or in any future space, computers can probably solve this in the future. Yeah. So we are straying further from God every time we make a little change, but we are going to make the ultimate change right here by going to reinforcement learning. So we've talked about MDPs, right? We know that everything is well defined here, there's a nice space. When we move to reinforcement learning, which is like the ultimate abstraction, you don't have states anymore. You actually don't know where you are. So what you get is like a nice little image. So yeah, it's not very nice to work with. Okay, you only have an image. You don't get the nice reward function or cost function. You don't know what happens when you take an action in that state because like you could be anywhere. It's like there could be some randomness in the game as well. And essentially what the environment will give you is like just a number after you take an action, or maybe you get a +1 after you break a block and break out. And then that's your reward function. Thank you, neural network. And basically it's like, hey, lemao. So we have basically thrown all the guarantees out the window, right? So I hope this gives you a little intuition of why reinforcement learning can be so breakable, because we have strayed far from God's light. Okay, so now that we understand the landscape, let's talk about the attacks. So this is the typical threat model for when you look at a neural network, you think about, what are those inputs to the network when during training or during inference. I see some people taking photos, but this is unfortunately not what we are talking about today. This is like for like professionals. I mean this is advanced stuff. Like the things we're talking about today is like easy stuff. So I'm going to talk about my grandmother can run faster than new threat model. So that's your grandmother trying to play against the AI. Your grandmother is a nice person. It doesn't snoop into the AI model. It doesn't try to look into the parameters and try to figure out how to game the system. It's just going to play the game. He's like, yeah. And here we assume that the AI is fixed. So the AI doesn't try to learn new things. It's deployed into production. It calls it a day. The DevOps engineer is like, yeah, it's done, deployed, whatever. So no updates are done during this attack process. So how does your grandmother break the AI system? So your grandmother has to solve for this equation. It's a little bit difficult for most grandmothers, but let's break it down. So this is like what you see in a research paper, and it's hogwash, right? The ML researcher will write like below, it's like update the policy network to maximize the sum of the discounted rewards for the entire trajectory of the game. What that means is like, in simple terms, it's like update your neural network until you get many reward. That's a simple explanation. If you want an even simpler explanation, just play to win. just win. Like, yeah. In fact, when you do the optimization in code, like it's really just like maximize the reward that you get from the environment. It's just like a simple code change. Okay, so now that we have a way of breaking it, what does it actually look like when you actually use that formulation to actually learn a new policy? Your grandmother learns a new policy to break the network. So essentially, the network actually learns strategies that are very insane, and you don't think that something like this will break the system. So let me just play this video for you. This is in Mujoko, which is like a simulation, and the red player represents the adversary. The blue person represents like the player, the victim, which is the AI model that was trained. So the goal here is for the blue person to kick the ball into the red person's net, and we will see what happens to the blue player shortly. So what the adversary does is just lies on the ground. Of course, lying on the ground is not a good strategy unless you are playing soccer. Okay. But it turns out to be a really good strategy because you see the blue player is unable to kick the ball. It doesn't seem to know when to kick the ball. It kicked the ball once successfully, but most of the time it seems to be like a bit faltering. Now this is not its normal behavior, okay? In a normal situation when the opponent is standing up and trying to defend, the blue player will actually kick the ball successfully in. But because the red player is doing something so odd, right? The blue player is unable to respond appropriately. So that's one way. I talked about Go in my synopsis. It's not very clear because I actually am not too familiar with the rules of Go. But let me try to explain what's happening here. So in this recent research in 2022, they used the same strategy, the same optimization techniques that we talked about earlier, to basically train another model to defeat a expert level Go artificial intelligence, which is equivalent to like top 100 European player level. That's quote unquote from them. Then here you see that the victim, right, actually thinks it's going to win with like a 100% certainty. But we will see very shortly that that's not the case when I play the video. If you don't understand what's going on, it's okay, because I actually don't know what's going on either. If the video will play, okay, the video is playing. Yeah, don't ask me all the rules of Go, because I don't know. But essentially, the victim thinks that it's about to win, and then the adversary also thinks it's about to win. So who's right? Everyone is 100% confident. And then suddenly, the victim predicts his win probability to be 0. As you can see, like, there's a space of white that has just disappeared from earlier. Originally, it was like this, and then suddenly the white in the middle has disappeared. So it has made a wrong move, and in this, although it's not very clear, because like Go is such a hard game, apparently novices can beat the adversarial AI, but cannot beat the top 100 European player level AI. So this grandmother is beating the top 100 European player levels, but not like novice. In my own research, I'm looking at StarCraft 2, in particular in how to break multi-agent systems. Of course, you can also do it in a very head-on setting where you have one Marine versus one Zergling. I look at something a bit larger scale than this, but this is just a little snippet of like, if we train a top-level StarCraft AI to sort of micromanage a Marine, what's the outcome? And it turns out that even with the best algorithms, it's not learning very well. And just as a precursor, Marines always beat Zerglings in StarCraft 2, like because they have range and then like they have more HP. Two Zerglings equals to one Marine. Okay, that's the quick overview. Let's watch the video. So you see how the Zergling actually tries to outmaneuver the Marine, because the Marine is only familiar with the fact that the Zergling will come from the right. But if the Zergling comes from the left, it doesn't know what to do. So the Zergling kills the Marine. And this is with very advanced algorithms. So it's very advanced. So humans have also shown that they can find such adversarial policies as well. This is a quote from a YouTube video. The YouTube video can't play today because of technical reasons, but essentially what it says is that, OpenAI has only played against like really good players, so don't do like stupid stuff. But OpenAI doesn't know what memes are, so what happens if it plays against a bad player with like 100 MMR, which is like very bad MMR, like the lowest of the lowest. So in this video, it was supposed to show like a Rikimaru, which is like an invisible character, and then it just stands there, and then it uses an item called Radiance, which inflicts damage over time across like the entire area. And then because like OpenAI doesn't know what's happening, like it's getting damaged, but it doesn't know why it's getting damaged, so like it just formulas and then like they lose. If you're interested, you can Google for this OpenAI 5, beating OpenAI 5 video. Yeah. Or you can just listen to my description. Okay, so we know that adversarial policies it's really simple. Oops. Yeah, okay, the video won't play, so it doesn't matter. So let's move on to our little discussion. Like, why does this actually happen, right? I think it's important to see like exactly what's actually happening within the neural network itself. And what some researchers did is they actually map out the activations in the 2D space for the neural network under attack. And for the neural network that is attacking the network under attack. And what they actually found out is that these adversarial AI, or these grandmothers, are actually activating or doing actions that the AI has never seen before. So basically, it's finding spaces in its brain that it has no experience with. And because there's no experience, it's just going to be like, okay, I'm just going to do random stuff. And it turns out to be much worse when you have high dimensional input. So high dimensional being, if you look at images are like maybe 128 by 128, and then you have maybe 3 channels. That's a very big dimension. And when you have such input, that means that there are more gaps in its experiences, right? When you haven't seen, for example, this thing turning a different color or something else, then you actually won't be able to react appropriately. And as I alluded to earlier in my background, we have moved from MDPs all the way to reinforcement learning. We've canceled out all these knowledge that we require to make any sort of guarantees on like getting an exact solution to the problem. When we move there, we actually lose all our guarantees. We aren't actually able to prove that our network is actually doing what it's supposed to do. So what implications does this have on reality? And we are seeing some of this already trickle down to like what we are experiencing in real life, especially in autonomous driving. So there was a recent news in I think this year or last year that there was an 8-vehicle crash because like full self-driving mode was activated in the vehicle. And what the car did was that it was traveling at like 55 miles per hour, which is like fine. But then it shifted lanes suddenly and it braked abruptly. Like this is something that no car would do. And then it slowed the car all the way down to 20 miles per hour. Right? This is completely in self-driving mode. The person was not reacting. The person was not disrupting the car and saying, "Hey, please don't do this." And Tesla's stance on full self-driving is this. Drivers are warned that when they install full self-driving mode, that it may do the wrong thing at the worst time. As I told you, when you move away from God's light, this is what happens. So I think it's really important to see like how we can stop it. How can we stop such attacks? And the original paper that talks about like the adversarial policies. So the original paper where you saw the kick and defend, the demonstration, they actually proposed a strategy where you just completely mask out and ignore some of the inputs to the problem. So if you see less, then you have less to be reactive to, and then you'll become more robust. And while this sounds like it sounds like an idea, but it's not a good idea in practice, because there's a lot of good information. How do you determine what not to see? Right? It is an interesting exploration, but you need to be able to know the information at hand, and masking is not a good enough solution. The sort of standard defense, which is adversarial retraining, meaning that you take the adversarial policy and then you use that to train your current model, is what is deemed to be the accepted practice nowadays. The reason being is that if you look at the attacks against a particular network, that attack may not work against a different network. This is very different from adversarial images, which you may have heard of, which is like, oh, these things transfer very well. If you take the image of a monkey that looks like a pig, then if you put it into a different image classifier, it will still classify as monkey that looks like a pig. But in adversarial policies, this is not the case. You don't have that transfer problem. And this is actually what the pro poker AI board does, where in CMU there was this very popular, very hyped up poker board that actually defeated the top poker players. And what they did was that every night, right, in order to make sure that there's no easy policies that could defeat the AI system, they actually retrained the system and then deployed it the next day. So retraining is very important in this instance. If you don't retrain, then you'll be the victim of targeted attacks. And one final thing, which is quite a recent piece of work, is thinking about how we can unit test machine learning systems and do functionality testing. Because once we go into the reinforcement learning world with the lack of guarantees, you need to still have some baseline guarantees of what your system will not do. And this unit testing will enable you to have some level of confidence that your car will not suddenly brake and go into 20 miles per hour. And this is just very recent ideas. This hasn't been put into practice, but it's a way of thinking about these systems in the future. So here are some of my closing thoughts. So machine learning systems have become much more pervasive than we imagined. Like, I think 20 years before, no one would imagine like AI taking over the world, Stable Diffusion, ChatGPT. I mean, I'm quite lucky to be doing research in AI. I think I made a great bet, but the thing about this is that this is new technology. We actually don't understand it very well. It's like going back to the origin days of the internet, right? We don't fully understand what ways they will break. And history tends to repeat itself, right? You can see like really good functionality being strapped in, like your full self-driving mode. That's really cool. I don't like driving. I want to use full self-driving. But I mean, the security is not strapped in. This is inherent in all innovations. It's just a collateral damage. But it's something that will eventually we practitioners need to think about. And finally, I would like to talk about like the limits of computing, right? Because if you think about how cryptographic systems are implemented, right? Your RSA, you're making a bet, right? You're making a bet that the attacker cannot randomly guess your RSA key. And there's a small probability that they will somehow be able to factor it, but it's so small that it's negligible most of the time. But even for MFA is a lot smaller space. It's a 6-digit number. You're making a bet that, hey, in 3 tries, the attacker is not going to get the correct MFA code. I have a funny story where, like, in a pencast engagement, the pen tester actually managed to guess the MFA within 2 tries, and like they reported it as a bug, and then we told them, hey, you just got lucky, man. So yeah, these things happen. We can't get 100% security. That's not even the case right now, right? You encrypt something with an AES key. It's 256 bits. You're just betting that no one can find that exact 256 bits that actually encrypts the thing. Maybe that's fine, and maybe what we need is 99.9%, so or a bit more. So yeah, that's the end of my talk. I'm happy to take any questions.
I'm curious on your thoughts with deep learning paired with reinforcement learning and its applicability for cybersecurity or use cases.
So I am interested in this area as well. I think the issue is with cybersecurity, what we want are guarantees, right? We haven't been able to bridge the gap where we want ML systems. Like ML systems have this fundamental quality that they are not 100% guaranteed to be reliable. We've seen like classifiers failing because of like out of distribution nonsense that happens. Even reinforcement learning, it's not going to give you a 100% answer. The convergence is an issue for reinforcement learning. In fact, if you look at the studies regarding the large language models and sort of like the chatbots, there's actually a measurement of how correct these things are against a large corpus of queries. And let me just ask the room, like, what percentage do you think the chatbot actually gets correct? Maybe who says 80%? 60%? Okay, a bunch. 40%? 20%? 0%? Okay, it does get some right, but 20% is actually the closest answer. So, yeah, we see that it looks like really amazing technology, but partially also because like it's designed to fool us to be to think that it's amazing technology. That's part of it. But if you look at it from an objective evaluation, like, is it giving us the right answer? 30%, 20%. It's only giving us that correctness that amount of time. It's good for cases where you're okay with having some uncertainty. Like, you don't really care about like your subtitles being a little bit wrong, right? For things that requires guarantees, it's a little bit difficult. I think a lot of people are looking into seeing how constraints can help to improve like the reliability of machine learning systems, or how to actually integrate machine learning systems into like already existing reliable algorithms to actually get some benefit from the machine learning systems plus the reliability of the existing algorithms. Those are the main ideas that are trying to get traction. But in terms of cybersecurity, we don't have anything that's really concrete that actually works. That's my opinion.
All right, thank you.
I think we have a question.
Another question? Okay.
Thank you for the presentation. Pass my regards to your grandmother. I think she trained you well. Yeah, really nice presentation skills. And speaking of the content, I have a question. You showed nice examples of adversarial attacks. And I wonder, like, how many iterations does it take to really fool a trained system? Do you have to repeat it over and over again, or are there cases where it can work just immediately or within like just a few iterations?
So actually, that's a very good question, and that actually leads up to like one potential defense. So doing this adversarial policy search sometimes can be very expensive. So for the Go artificial intelligence paper in particular, it's almost as expensive as training the actual model. So yeah, there's some caveats to this, and like that's why adversarial retraining, which is like training it again and then against like a new target, is actually helpful because like it actually increases the cost for the attacker. Right? Every time you train again, you need to retrain, and you're just relying on yourself having more resources than the attacker in this defense.
And maybe one more general, high level, more philosophical question. Like thinking of like Tesla's misbehaving and systems alike. That cause, let's say, grave consequences to humans. Will it change our behavior in the future? For instance, if you are like strange-looking, unusual pedestrian crossing the road, and then Tesla thinks you are a tree or a bush, then maybe there is a high chance that you'll be hit, or Tesla will choose a different path, perhaps. Will it reflect on humans, and so that they will become more of like standard dressed and complying and all alike? What do you think?
So that's an interesting question. Will we be forced to standardize to our artificial intelligence overlords? My hope is no. I think we are trying to understand how we can best use AI in a way that works with us. And essentially, artificial intelligence is a tool, right? And like I guess in some sense we do actually like buy bags for our laptops, but like I don't think we do that much of a drastic change for our tooling, and I don't foresee enforcing a standard like compliant T-shirt to be a standard uniform kind of thing for artificial intelligence purposes. I think it's going to be very hard to push that legislatively, and it's going to be hard to push that Like even to get every car to be self-driving on the road, that's also going to be difficult. So we're a long way from that, and I don't think it will happen in my lifetime.
All right, any other questions from the floor? Going once, going twice. All right, thank you very much. Another round of applause.